good afternoon or good morning, whichever the case may be for you. So what I want to do today is talk about what we learned by doing those stations about sound. If you're in second period, we did that on Tuesday. If you were in sixth period, you did it with Mrs. Taylor and Mr. Borcherding on Wednesday. If you were in fourth period, you did it with me yesterday. What I want to do today is I want to talk about what sound is and summarize what we learned in those stations, and we're going to kind of go over a lot of those stations. So I want to start with that. So I want your notebook out. I want you to title page of your notes, Sound. And the first thing that I want to do is I want to talk about what sound is. So what I have here is a simulation, and when you're looking at the simulation, I want you to think about the station where you had the speaker, and you could change the frequency of the speaker, and you were trying to see like what's the lowest sound you could hear, what's the highest frequency sound you could hear. But what it was is that speaker, if you could particularly see this at very low frequencies, all that speaker was doing is vibrating back and forth like this, right? So you can see here in the simulation that the speaker cone is vibrating backwards and forwards, and these particles here are supposed to represent the particles in the air, right? And the idea is that that speaker cone pushes back and forth, it pushes the air back and forth. Now this, if you recall from last unit, there's a type of wave for this. So this wave is generally going in that direction, but the particles are moving back and forth. And if you recall, that's what we call a longitudinal wave. So the first thing that I want you to have in your notes is this. The first thing I want you to know about sound is that sound is a longitudinal wave. And since it's a longitudinal wave, it has got to have something to travel. Let me see if I can zoom in. All right, so sound is a longitudinal wave, and since it's a longitudinal wave, you have to have something to vibrate, right? So sound is going to be something that must have a medium to travel. So sound must have a medium to travel. What I mean by that is, if you've ever heard that old saying from the old movie that in space no one can hear you scream. So in outer space, sound doesn't exist because you have to have something. If I go back to my animation here, you have to have something that you can push back and forth to make a longitudinal wave. But sound does not, so the most common place when we experience sound is in the air. But you don't have to have air in order for there to be a sound wave. Sound travels through all different kinds of mediums. This was the station one you did. This was, there was some reading you did out of the book. And some things that you should have noticed in the book is that sound can travel through solids, liquids, and gases. And sound travels faster through liquids and solids than it does through air, which is a gas. And the reason that is if you think about this, right, if I go back to this animation, that's, well, I'll leave this up here so that you can type it, or so that you can make sure you copy it down. But the reason why that is if you think about sound waves, you think about those particles on that simulation we just saw a second ago. Those particles are pushing each other to set up a longitudinal wave. If you think about what you know from like middle school science about solids, liquids, and gases, gases are the material that have the particles spread out the most. So sound actually travels the slowest through gas like air. It travels faster in solids and liquids. So sometimes you'll see, if you ever watch any old westerns, you'll see one thing that if they're looking to for listening on the ground for the sound of horse hooves, the idea is that the horse hooves are going to get to them faster. That sound is going to travel faster through the ground than it is through the air. So that's kind of an application of this. But sound travels faster through liquids and solids than it does through air. It's just that we happen to live in the case where we're breathing air most of the time. So we usually hear sound through the air. The other thing that I wanted to say about this is within those things like temperature might affect it. So it turns out that sound travels faster through warm air than it does through cool air. Or the density will have an effect. So sound would travel through a really dense material like metal a lot faster than it will travel through a not very dense material. Like, let's say, for example, wood, right? Wood does transmit sound, but doesn't transmit sound as fast as metal does, because wood is not as dense. All right, so you have to have a medium for the sound to travel, and then if you get a medium that's more dense, maybe that's moving, in which it's a little bit warmer of an air or something, then the sound travels faster. Those are some things about sound. The next thing that hopefully you learned about sound, I want you to think again to the station where you were turning the dial and changing the tone on the speaker. So as you change the frequency, that pitch changed. Right? So let me actually see here if I can find an example for that online. I should have had this pulled up. Let's see here. But here's this. So I'll just, if you'll listen here, so 440 hertz, if I increase the frequency, you hear that it's going higher and higher, right? And you saw this too when you were playing with the dial on the I pushed the wrong button. You saw this too when you were playing with the dial on the speaker when we did the stations. So here's the next thing that I want you to write down about sound, is that the pitch of the sound is determined by the frequency. Or I guess more to the point, we can say we, as in humans, perceive the frequency of sound as pitch. You get a higher pitch sound if it's a higher frequency. All right, now I want you to go to, I want you to think about this next station that we did, which was, well, there were two that talked about resonance. But I want you to think about that one where you had the tube and you changed the length of the tube and then you hit a tuning fork and you were trying to find the resonant pitch. And, or the other thing you can think of is the Mythbusters that you watched the day after you finished the mini test. You had the Mythbusters where the person was singing, and when he sang the correct pitch, he was able to get the glass to break. So I want to define a few terms for you here. So the first term I want you to define is resonance. And I'm going to show you something here real quick. So here's what I want to say about resonance. When an object is forced to vibrate at its natural frequency, its amplitude increases. I like to draw for you a little diagram of this. If I make a graph where I put frequency on the x-axis and I put amplitude on the y-axis, there is some frequency, we'll call it the natural frequency right here, that causes resonance, that causes the amplitude of vibration to be larger than every other frequency, right? So what this is showing is that if you try and force something to vibrate lower than its natural frequency, no resonance happens. If you force something to vibrate higher than its natural frequency, nothing happens. But if you force it to vibrate at its natural frequency, it's going to increase the amplitude of the vibration. Now, where do you see this? So the most common place to see this, and I'm going to see if I can pull up a video here for you in a second. But the most common place to see this is in a swing, and your book talked about this. If you are, when you pump yourself on a swing, or if you've ever pushed a younger brother or sister on a swing, you know that you have to push the swing in time with the natural frequency of the swing. And if you don't, the oscillation, right, how high you're going on the swing, does not get higher and higher. So let me show you this here. Let me pull up a demonstration. So in essence, what I've got here, can you hear me? I gotta make sure it's recording. Yeah, it's recording. In essence, what I've got here is a model of a swing, right? This is what we have been calling a pendulum before, right? And the idea is, if you have a pendulum, if I want this pendulum to resonate, I need to push it every time that it gets over to this side. If I push it every time, I just give it a little push every time that I'm back here, it resonates. It gets going higher and higher. If I push it at a different frequency, so let's say I decide to push it twice as fast, right? If I try and push it faster than it wants to go, right, I'm not getting resonance. It's not going higher and higher. It's not really having much of an amplitude, right? So swings can have resonance. You see that with this pendulum. You see that when you pump yourself with a swing. But so do things that are oscillating a lot faster. And that was what you were seeing when you had the tuning fork and the tube. You were changing the length of the tube, and that changed the natural frequency of the tube. And when you found the right natural frequency, you were causing resonance in the tube, and you were increasing that amplitude. So looking at our notes, that was the part of the graph where the amplitude is higher because you're playing the exact right frequency. So that's resonance. Resonance and I had one more animation I wanted to show you that I pulled up here. So you can look here. This is a spring. This is a simulation of a spring. Let me see if I can zoom in a little bit for you. And the idea is right now it is not resonating its natural frequency, so it doesn't oscillate very much. So this is the oscillation up here. If I increase the frequency, so I'm going to bring the frequency up to, pause it here, up to 3.33. Can I change that here? Let me see. How do I change it? If I increase this frequency to 3.33 and then start it, you'll see I'm going to get resonance. It's going to be going faster and faster, right? Because the idea is I'm pushing it up and down at the same frequency that it naturally wants to go at. If I do it at a different frequency, go back to 2, it doesn't resonate, right? Because it wants to go, this is saying here, it wants to go at 3.16 hertz, basically. And I'm oscillating it at a different frequency, so there's no resonance. So that's the idea of resonance, and you heard that in the resonance tube. You also saw that in the machine where you were changing the dial and then the different bars resonated. The next thing that you talked about, the last two stations, were about the phenomenon of acoustic beats, and that's the last thing that I wanted to find in your notes for today. So acoustic beats occur when you have or you play two frequencies that are very close to each other but not exactly the same. So this was the wobble that you were hearing when you were playing the two tuning forks. So when you remember, you could adjust the one tuning fork and it started out, they sounded the same, but if you got it a little bit out of tune, you were hearing a wobble. That was the idea of acoustic beats. I'm going to show you an animation of why that occurs. So beats occur because of constructive and destructive interference that we talked about last unit. Now sound is really a longitudinal wave, but I think it's easier to see on a transverse wave, and that's what this animation does. So if I play two frequencies like this that are the same, right? Those two waves are on top of each other. They're totally on top of each other, so you actually can't even see them. So this is going to be constructive interference. You're going to get a bigger wave. But look at what happens if I get them off a little bit. So you see what happens if I play two frequencies not quite the same. The red wave and the blue wave have certain areas where they overlap, like they do here, and certain areas like here where they don't. And so you have areas of constructive interference, then destructive, constructive and destructive. And the result is you get a wave that's bigger and smaller, bigger and smaller, bigger and smaller.